anything, which means that so, there. Kyle, can you hear me? That's probably what the problem.
Yeah, I can hear you.
All right. So you couldn't hear me before. All right. So what did I just downloaded the thing right from here. Let's see the download. Where's the download thing? Is this a new one? Hopefully it's a new one. All right. So oh, the homework. All right. So the homework. We'll put up a new homework. Homework 7. Homework 6. One group didn't do A. If you don't do it, if you do anything, like you get points, if you do nothing, you're kind of risking 20 points off. So like try not to leave something blank if possible. Then D, it says, what power laws do you expect? So this thing, all right, this was a problem. So if you, one group down Igor and then got the plot and looked at the plot. But if you didn't do that, so you guys didn't do that, right?
Yeah, because I try the Igor, I don't say
Okay.
on my side.
Anyway, then in that case, you should have said like this figure 4 PDF isn't working. And I fixed it, but basically after the fact. So this would have answered your part D problem, Or you could have emailed me and said the Igor is not working. You should have emailed me at that point. Anyway, it wasn't that many points, but basically so the data is like this. You can digitize this data using something called Igor Thief. It's a program inside Igor, and you can digitize the plot, and then you can subtract off this background, the flat background, which is, they even say it's an incoherent background. So it's something, but anyway, even if there's no incoherent background, there's always a background and scattering, because this is going to go to diffraction over here. So there'll be an amorphous halo or diffraction peaks, and that's got like Compton scattering or something like it. So there's always going to be a flat background, even after you subtract all your, so if you run the solvent alone and the polymer alone, then multiply them by the percentages and subtract those from the thing, you still will have a background. So you have to, there's always going to be this flat background here. And if you don't subtract off the incoherent, so they didn't subtract off the solvent, basically the incoherent solvent. So there's a definite flat background. They didn't bother to subtract. If they had subtracted it, they'd find out that it's power 2 out here, 5/3. So that's the thermal blob thing. Right. I mean, the data has the thermal blob signature right in it. And this is a blob size here. And then inside the Igor experiment, I actually plot the blob size versus I think these are different concentration of the heptane. And you can see that it's linear. Like the blob size ends up being linear with the heptane concentration. It's in the Igor experiment, it's not in this thing. But so anyway, that's what. So what power do you expect at low and high Q? So if it's a thermal blob, you expect it to be good solvent at the at large sizes, and then at small scales, it collapses into the Gaussian. So it goes 5/3 at low and 2 at high. That's it. Comment on figure 3C. So he proposes this as a switch from good solvent to, and it isn't, because this plot shows you that there's a trend, there's a trend in this blob growing so that the thing becomes collapsed. That's about it for that thing. I mean, everyone did pretty well, except you're right, D, like people didn't do that great on D. Half the people did good on D and the other half didn't. So it didn't matter that much. Basically, it's complicated, so, and you can get confused pretty easily with this stuff, the blob thing. And also people tend to ignore it. You can see he just breezed through it, even though they're kind of like, this is their stuff, like Higgins was kind of friends with the Jens and Edwards. They were all like in a club. So they should have done this, like there's not really a reason except that they didn't bother to look at it that deeply. Anyway, any other questions on this quiz or homework? I thought it was okay. Everyone did okay, I thought. So, all right. So anyway, we're back here. Doing this intrinsic thing, intrinsic viscosity. Let's see, hide floating controls. So we went through this, like that you can calculate this hydrodynamic radius. It's going to be an average, it's a transport number. So it's like the equivalent spherical size of an object that has the same drag coefficient, right, of whatever it is. And in this case, it's a Polymer chain, right? Or if it's a sphere, then that's actually the radius of a sphere. So it's Polymer chain, it's the end-to-end distance by the square root of 6. So it's smaller than the end-to-end distance of the chain. You can calculate it because it's averaging the diffusion coefficient, and the diffusion coefficient 1 over the thing end up as this this harmonic mean of the thing, which weights the small things larger than the big things, which means you get a smaller number than the RG. And it kind of flattens out because the small things are kind of the same as temperature goes up. But then when it becomes a sphere, RG is smaller than the sphere radius. So this becomes a sphere radius, and the RG is 3/5 of the sphere radius, square root of 3/5 of the sphere radius. I think it's 0.77. Right, so that ratio of those two is 0.77 here. Now here it ends up being like 0.5 or something like that. So 1.5, I mean 1.5, not 0.5. And then for other objects like branch, you can get different ratios. This RH to RG ratio, people use it as a test to see what the material is, see what the thing is. Let's see. Then we went through this idea of intrinsic viscosity, which is based on this equation, which is called the Einstein equation if the intrinsic is 2.5. So this will have a value of 2.5 for spheres, right? And if this has a fixed value like that, this just shows like what's going on here. Like you start with a viscosity measurement, and then this is entangled out here. You get to the solvent dominates, right? So you have no slope there. So if you subtract off the solvent, then you can see, so this is like the background subtraction with the scattering. Then you can see this power 1, which means that you have an additive effect of the polymer. It means that the whole polymer is acting like a sphere moving through the fluid, as if it was a sphere. It means it's non-draining. So it's draining and non-draining. If the chain is non-draining and it's acting like a sphere, then you get this linear addition. If it's draining, then you have a Zim behavior, and it's going to have this molecular weight dependence that's linear. So both things are linear. One is against viscosity versus molecular weight, power 1, and the other is viscosity versus concentration, power 1. So this is a non-draining Zim behavior. So the polymer is acting like collected all the stuff. The other one is Rouse behavior, where the chain is totally draining. Like it's just the solvent isn't attached to it at all. So it's just, in that case, viscosity just adds up each mer you add on, you add one more viscosity kind of unit of it. Right. So anyway, those are the two kind of things people talk about. Like Zim means this plot. It means that the thing's a ball, the whole chain's a ball. And then Rouse means the chain's independent mer units. Right. So it's totally draining and non-draining. Those are the two. And then actually you have in between those two is a real world, and that's kind of what you call the hydrodynamic effect, and things get dicey. It's hard to calculate. like what the hydrodynamic effect is. In the paper this week, he's talking about water binding to these dendrimers, so he's got these kind of highly branched things, and then they trap the water because they have an affinity, they're hydrophilic, so they just trap the water in it. So then the water, and you can put that thing in a DSC and see the water separate from it. Like you heat it up and the water has enough kinetic energy to break free from this hydrophilic polymer. Anyway, so you can see like that can get pretty complicated. In other words, this draining, non-draining can be temperature dependent or solvent dependent, or a lot of things dependent, like any kind of witch doctor thing you want to come up with dependent. So anyway, things get kind of interesting. Also, kind of like it becomes more and more you're making things up the more you get into this, right? So because you can't. But anyway, the simplest case is this Einstein equation, which would be like this is a fixed number, and it's for a sphere, so it's 2.5 as a number. And in that case, you can kind of say, well, what is that? What is this equation really? So it's just a simple displacement of the fluid. So if you say your shear rate is the strain, so the shear strain, so the change in x as a function of y. It's like if you take the length, you change in x, and then the distance y. So you got a deck of cards, move the top card certain distance, and that's the stack depth. So you take the ratio of those two, that's the shear strain, right? And if you do that continuously, then there's a rate of it. It's like a velocity, like delta L over dt is a velocity of the top card. So you have the rate of strain change, right? So the change in time's kind of that's not a thing you want to mess around with. Better to leave time alone, and then this Ly and the delta L by dt, that's the velocity. So this Ly you can kind of consider in a construction, as something that could change as you add stuff to it in this way. Like the total Ly, and the Ly gets smaller by a function like this, like you add stuff. So the concentration times 2.5, and then 1 minus that, so this L star gets smaller the bigger the concentration. So it's just displacing the fluid. So your strain rate effectively increases because it's a ratio that delta Lx over Ly gets smaller, the strain gets bigger, right? So how do you get that from this? So you take this thing, you say, well, if this is small concentration, low concentration, which is, you need low concentration for intrinsic, then you can say, you can swap this for an exponential. So this exponential expansion would be like the argument, then plus the argument squared over 2 factorial cubed over 3 factorial. So the first two terms, because it's small, you can just say that's exponential. Then if you plug this viscosity in here, you find out that you have exponential divided by Ly. So Ly becomes, the new Ly is Ly divided by this exponential, Ly times exponential minus. And then if you expand that out, because this is small, you get 1 minus that, which is that thing, which means it's just a displacement law, right? So it's important to kind of see this for what it is. This is why Einstein thought this was stupid, because it's just like a displacement law. It's just like a simple, this stuff, all right, so if the stuff's floating around, or if the stuff settles all to the bottom and makes a concrete brick thing at the bottom, you get this same behavior. It doesn't matter if it's floating or not floating. It's just displacing the fluid, right? So anyway, so I guess that's why he thought it was stupid. Anyway, it turns out this is like for solutions of colloids and polymers, this is like the main game, even though Einstein was embarrassed by it, so nonetheless, yeah. So anyway, so what is this thing? This intrinsic becomes like how adding something to the system, how much volume it takes up, like when it goes in, right? So that's the same as C star. Like in other words, the mass divided by the volume is the concentration of one of these things. So 1 over that C star, and then this times the concentration turns into unitless, and then that gives you the thing you want, which is like just the solvent viscosity times some modifying factor. The viscosity goes up as you add the stuff, right? So that's the general theme of this. And this intrinsic is going to be just it's going to be basically inverse of phi star, which would be like the mass divided by the volume of the coil. And the volume of the coil depends on the mass by the fractal dimension. In other words, that's the density of the coil. So the fractal dimension gives you the density. So the volume is going to be 3 divided by df. So the mass to the 3 by df, and then divided by the mass gives you 3 by df minus 1. So this thing should depend on the molecular weight of the chain, 3 by df minus 1. 3 by 2 is 1.5 minus 1, so you get 0.5. So mass to the 0.5. Molecular weight to the 0.5 would be for a Gaussian chain. If you put in 5/3, then that's so you have 5/3 1 over, let's see, what is it again? 1 over 5/3 minus 1, which is 0.6. It'll give you 0.8 if it's an expanded coil. And if it's 1, then it's 3 by, you end up with 2 for this, power 2 for a rod. And if it's 3D, you get power 0. So 3 by 3 is 1 minus 1 is 0. So you get m molecular weight to the 0. So this doesn't depend on mass if it's a sphere, because it's just a displacement. So it doesn't matter. The sphere is going to take up the same displacement. It's just matters like what the concentration of the spheres are. They'll do the same displacement. Solid objects will just fill it like bricks. So you don't need to worry about the dimension of these objects at that point. So it all kind of works out nicely at low concentrations. So this business of the intrinsic is like you take the viscosity minus the solvent, and then that will give you, let this appear, this kind of Zim behavior appear in concentration. And then if you normalize by the solvent viscosity, that becomes a unitless number. And then when this number is at 1, then that's where the transition to entangled shows up for an unproven empirical observation. Right, so the 10 to the 0 on a log-log plot, and you look over and you see a transition in the slope, that's entanglement. That's like rheologist's definition of entanglement. So, and then if you take this to 0 constant, so if you divide this by concentration, take it to 0 concentration, that's the intrinsic viscosity, which is a number that has units of inverse constant, so 1 over C star. So intrinsic viscosity is not a viscosity, it's 1 over C star. It's like the density of the coil in the framework of this flow field thing, density of the chains in the coil. Right. So anyway, so in that process, you invented all this stuff, right? All these terms, like the relative viscosity is a ratio of the two. Specific viscosity is the difference divided by that. The reduced viscosity is that divided by concentration. And the reduced, when concentration goes to 0, gives you the intrinsic. I can never remember these names, but basically this kind of picture might help a little bit, right? And then this idea of displacement is important to have, because that kind of tells you what's going on, right? So that's that business. Then so then you have this thing of what happens when the concentration goes higher. So you have this behavior that's going to go to this entangled regime. I mean, the simplest case, it's going to go to entanglement. Okay, so you're increasing concentration, boom, you get this thing. So this part you fit with that linear term. So people wanted to be able to fit the higher orders, so they just did a Taylor series expansion of it. Right, so concentration squared, cubed, whatever. So that's kind of a bulky equation. You have to truncate it somewhere. So then in order to solve that problem, so you have the linear part, you want to keep that. And then you have the second order part, which would have the concentration as the front end, and then just say 1 plus this thing plus that thing looks like it's an exponential expansion at low concentration. So you have 1 plus K1 times intrinsic squared. So you'll end up with an exponential from this thing. And basically, you could describe that with an exponential. So that's the Martin equation. So there's a lot of this expansion of the exponential in this game. So this is one way to do that, the Martin equation. Then there's just take the first two terms of the expansion, the Huggins equation. And then there's like do a weird, just do a exponential expansion of all this whole thing. So this would be like intrinsic, so exponential of intrinsic, but take the first two terms. So then take a log of the reduced viscosity, which I'll have to remind myself is this thing. So in specific divided by C. Anyway, there's different equations people come up with. This Kramer equation. Depending, and a lot of this is in biology. People are looking at these kind of equations to describe solution viscosities. We don't really need to dwell on these. At some point, there's so much literature on this. At some point, I just said, like, I'm just going to put everything in these slides. There's like too much in here. There's a book on this. I think it's on the webpage. It's Collecting Claisen Viscometry, relatively recent. This is, it's like you have the linear behavior, the Einstein behavior, and then the deviation when you get to entanglements. And then you can, this paper, they calculate C star as 2.5 over the intrinsic. And the intrinsic meaning they call it C star, but this would be 2.5 times C star, at the actual C star. And then they get this line, they say that's where it would deviate. And they show it's linear below that for whatever this stuff is. So this shows that this behavior changes with solvent quality. So the amount of entanglement changes apparently when you change the solvents. That's one thing. And then this is the molecular weight. That's kind of obvious. That's going to be the 3 by df minus m to the 3 by df minus 1 thing, which is that's the Mark-Hoenk equation. So Mark-Hoenk would be that the intrinsic viscosity equals K. There's two Mark-Hoenk coefficients, K and A. So K is a prefactor, and then the molecular weight to the A. Then A would 0.5 would be a Gaussian chain, 0.8 would be expand coil, 2 would be a rod, which would be like a protein, and then 0 would be a solid object if A is 0. So you can, if you look at those numbers, the K and A's are tabulated in like the Polymer handbook. You can Google them for different things, Mark-Hoenk coefficients. They also call it Mark-Hoenk Saruda. Saruda showed up later on. I don't know what Saruda is. Mark's Herman Mark. I don't know who Hoenk is either. So, but basically, I always call it, I mean, it's been called Mark-Hoenk. Anyway, then there's the different viscometers. I guess we talked about that. This is just showing that 3 by df minus 1, the Mark-Hoenk in terms of fractal dimension. And then let's see. Right, so this is our penny pan, the thing that phase separates, just like the PVME at around 30 C. So kind of like body temperature, the bio thing, we had a homework on that. So showing like, oh, there's a temperature dependence to this solution viscosity. Like this is, forget what these things are, but that one's penny pan, and the reason that it takes a dive is because it phase separates out, so it's crashing out of solution. This is kind of a non-issue. And then this is water. I think the bottom one's water, the top one's a different acrylamide. It doesn't have a phase separation, just showing that it's got the same kind of behavior in temperature. So, and then this is a phase separation. So what is the temperature dependence? So the temperature dependence is this Arrhenius thing. So if you take the viscosity of a solution or any viscosity, right, and then it equals the viscosity at some reference temperature, like 25, and then exponential of an activation energy over KT. So this activation energy is the energy. So you can take the viscosity divided by a reference temperature viscosity, and that's called a sub T. So that's the shift factor. Yeah, thanks. So that's A sub T. So you can do it with modulus too. You can, like, a modulus divided by modulus of temperature, the ratio is a shift factor. Good, thanks. So that generally will behave like this. So for anything, right? Basically everything in the world, and especially like water. And the problem is like the zero temperature for this thing, right? You're saying is absolute zero. In other words, the motion stops at absolute zero. But for polymers, and a lot of things, motion stops at the glass transition temperature. So this isn't exactly perfect for things that, or where the motion you're looking at. I mean, even in a glass is still molecular motion, like it's vibrating, it has temperature. But basically the motion of flow ends at the glass transition temperature. So you're not going to see exactly flow in your lifetime, right? So anyway, so anyway, this temperature has a problem, right? And then the way this has been kind of interpreted generally is that this E is an enthalpy of getting over a barrier. So it's as if you had a bunch of spheres, and then there's one sphere trying to squeeze in between the other two, and it has to push the two apart. So it's the energy to push them apart, and then it can pop over. So it's flowed.
Is it not the activation energy?
It's an activation energy, but it's usually an enthalpy. Like it's just one number. No, energy has two numbers, entropy and enthalpy, right? But it's usually dealt with as if it's an enthalpy, just one number, and no temperature, no temperature dependence to that. Like enthalpy is just a number. The entropy has a temperature in it. So that complicates this equation, right? So you'd want this E to just be a value, right? Not temperature dependent. So it's just the value, the energy that it takes to push two things apart and then have the other thing move through, right? So that's really an enthalpy. In other words, there's no organizational feature to it. You don't consider that you're rearranging the spheres when you push the thing through the hole, right? So if you do rearrange the spheres or something else happens like that, then you have to consider the entropy of it too, right? So if it's just one number, it's enthalpy, even though it's called energy, activation energy. So that's this simplest behavior is this thing. So, and then you have the WLF equation that people use for polymers, which has three constants, C1, C2, and TR. So this will give you that shift factor for like modulus, frequency. If you're vibrating it and you change the temperature, then you can normalize the frequencies by this AT factor, right? Or it's also going to be AT for viscosity, like how does the flow change with temperature for a polymer, right? So, and then TR is generally thought of as a glass transition temperature, which is kind of a hint. So in generalized, so that's in polymer. So Williams, Ferry is the guy, he wrote a book on polymer rheology, right? So he's like the godfather of polymer rheology. Williams wrote a book on mechanics or something, I think, and Landell, I'm not sure who Landell is. I think he might have been a student of Ferry. So Ferry was I think at Princeton, and Williams Landell, I think, are at Wisconsin. So these are like the rheology hubs of the world or something, you know. So anyway, so WLF is a well-taken equation, right? So and you can get that shift factor from it. So ratio this viscosity over the whatever reference temperature viscosity. So and it's in a log scale. Log, no, it's not natural log, not exponential. So you have to do this 2.3 thing to shift from the two things. But so if you take your Arrhenius function, which normally would be like an enthalpy, then you say, well, I got to take care of this temperature problem because absolute zero isn't right. So I stick in what's called a Vogel temperature. So this is the American approach. This is a German approach. And the German approach is kind of like glasses. Like they aren't exactly looking at polymers, even though polymers are kind of glass. So there's a Vogel temperature. So you add one other parameter. They have two parameter model. This has a three, C1, C2, and TR. So the problem with this is this doesn't mean anything. It's just an empirical function. Like there's no thought process to this equation. It fits the data well, you know, basically.
The universal constant, right?
Yeah, but they're winging it. It's just winging it. It's like, oh boy, this thing kind of works. Let's use this, you know. So this is better, okay? I'm showing you a better way. So this thing makes total sense. You have the balls, they have to move out of the way. There's an energy, and that makes sense. That's how everything works. This kind of, right? So in terms of temperature, behavior, and kinetics. So you have to put this in because of the glass transition or whatever activation temperature things happen at, right? So you throw that in, so your temperature scale becomes T minus TV. And then instead of just enthalpy, you say, I'm going to have an entropic component to that too, right? So then instead of EA, it's HA minus TS, okay? And there's just organizational features to moving the balls around. So this also has three parameters, 1, 2, 3, and this has 3, 1, 2, 3. And they're both describing the same thing. This ratio is AT, except this is in natural log and that's in base 10 log. So if you want, you can like compare those two and say exactly what C1, C2, and TR are. Like, what are these things? So that are just winging around. So the Vogel temperature, like where things stop. So Vogel temperature is well defined. It's where the motion stops. This TR isn't defined at all. It's just like some empirical thing to fit the data. So it's where things stop is C2 minus TR, if you work it out. And then this entropy is C1 times this log conversion factor, base 10 in base E. Then the enthalpy is C1 times TR to this 2.3.
You get the same values.
Yeah, of course. I mean, it's the same equation. It's just rearranged.
Okay.
It's exactly the same equation. Just this is in base 10, this is in base E, and then that's it. And then basically it's rearranged. They're the same equation, right? So that's kind of the point, that there is like a physical meaning to this thing, you know. It's got to do with enthalpy, entropy, like the things we're used to, and in a Vogel temperatures is where things stop. This is a more physicsy description of what's going on here. Because then you can measure these things, right? I mean, you can have an understanding of what entropy and enthalpy and why those would change. C1, C2, like you're on your own, like doesn't mean anything. So anyway, so that's one approach to look at this temperature dependence of viscosity in general, and of solution viscosity, of any viscosity, right? So there's that business. Then let's see. So Simha was a guy from Case, and I knew him, like he was this really old guy, 94 or something. He was like incredibly old, but like really bright and fun to be around, but like so old. Like anyway, he died in 2008. He must have been like 120, because like he's been around since a long time, you know, like Herman Mark, those people in World War II, like he was there then, and he wasn't a young guy then. So he went from, if you read this Physics Today thing, it gives his whole biography from when he died in 2008, but it's kind of an interesting story. And he did a lot of things. He invented the free volume theory for glasses. Then he carried that up to Case, and there's a guy named Jameson at Case that kind of took that further to measure free volume with positron annihilation and things for the glass transition temperature and things. Anyway, so he did, early on when he was in Vienna, I think he was also some refugee from whatever happened, you know, but might have been World War I. So anyway, he was doing this stuff with this, kind of looking at colloidal particles. Like in this thing, it says he was extending the Einstein equation for different kinds of particles, like tobacco mosaic virus and whatever, biological things. Anyway, he's got a ton of equations to talk about different shape, prolate, oblate, to get this, how this solution is, like, what is this intrinsic viscosity for these different shape things, you know. So at some point I thought that was interesting, but maybe now it isn't so interesting. I mean, if you need it for some basically biological things, and that's the thing to look at. And then there's the shear rate. The shear thinning happens in solutions, right? So there's also the shear thinning behavior that can happen with polymers. And also, so in the paper this week, you'll see like shear thinning happens with linear polymers, but it doesn't necessarily happen with dendrimers. And that there can be advantages to that. So this paper is about like what the advantages are in a biological medical context of not having shear thinning. In other words, if you need to inject something into a joint, you want to have low viscosity for the injection. You don't want to have to use a hunker large needle to go into your knee, you know. So basically, if you don't have shear thinning and you want to have low viscosity in the joint, apparently, to match the biological, the synovial fluid. So basically, having shear thinning isn't a good thing in that case. In most cases, it is a good thing, because if you have an engine, when it's running high velocity, you want to have low viscosity because it'll heat up too much and it'll burn the oil. So then you'll have no viscosity. So if it thins, and you're lucky that the thing won't burn. And then when it's slow, you don't want the oil to leak out. So you want it to be thick. You want to have high viscosity, right? So this shear thinning is perfect for an engine oil, but apparently it's bad for a knee joint. You know, so anyway, there's various situations where you might want this or not want this shear thinning behavior. Generally, in polymers for lubrication, you want it. Then all right, so there's a ton of stuff in here. So basically, if you look at that linear, and this is important to the paper this week too. So the intrinsic should be linear in molecular weight, and the slope, if you do a log, and the slope should be the Markowitz coefficient A, right? So, but if you have highly branched, there's this problem that it doesn't go linear, it tails over as molecular weight goes up, because the density of a branched object drops as it gets larger. So it isn't a constant density, and intrinsic is a density. So the density changes and the viscosity is going to change. So, and it gets even worse with dendrimers, like what we're looking at this week are dendrimers, and they have this weird behavior. So they can not only not continue on a linear, not go plateau, but actually drop at high molecular weight. So they have, this is called a peak behavior, right? So, and that also, you see the same kind of behavior for a different reason in polyelectrolytes, whereas you go to high concentration, you salt out the charge, in other words, this would be a slope of 2 for a rod, and it's a rod because the charges are forcing the thing to line up. It's got a huge persistence. But as you add more polymer in concentration, you add in the counter ion also. So you salt out the polymer as you go to higher concentration. At that point, it goes from a rod to a coil. Then this intrinsic drops from a power 2 to a power 0.8 in molecular weight. So the whole thing gets messed up with polyelectrolytes. It's a lot more complicated, right? So, and a few people have looked at it, particularly Colby at Penn State's looked at it in depth, you know. So let's see. So yeah, so we got branching this to look at, but that's probably good enough. And then the branching, so you can look at this in terms of this kind of fractal model if you want to calculate what the fractal dimension would be as the branching increases. And then you can kind of predict this behavior of low density. It's difficult to predict the dendrimer thing. That's complicated, like why basically it changes into solid spherical beads when it gets to high molecular weight. And a low molecular weight is more like a linear polymer. So you can see it's matching a linear slope, and then it goes to this, basically it goes to beads, you know, at high. So anyway, then when people talk about this branching and how to describe branching and then fluid flow, they go to this thing. So they talk about this G factor, which is the ratio, originally the ratio of the race gyration squared of the branched versus the race gyration of the linear, and linear is bigger than the branch. So this thing's below less than 1, right? So you have this G factor that's less than 1, and people have theoretically gone to get F is the number of arms, like the number of branches. So basically, you can kind of theoretically describe G in terms of number of branches. And then in terms of intrinsic, they have a branched and a linear intrinsic. They get this G factor for viscosity, and then they found out that this G factor from like static scattering, we get raised gyration, is related to the viscosity one by a factor of 0.58. This shows that from this paper. So you can see the prediction of just saying this thing would be like that line. Then these are measurements done of intrinsic, and then shifting this thing by 0.58 gives the right fit to the thing. So these are in this. So Jameson's another guy from Case Western in Cleveland, and Jameson kind of took over the free volume thing with positron annihilation from Simha. And Utraki also worked with Simha. So you can see these things are all tied into Simha somehow, back to this old guy who's dead now, but you might want to read his bio. That thing is a link to it. He's heavily involved in all this stuff. All right, so polyelectrolytes, I'm going to skip for now. We can talk about that. I wanted to talk a little bit about this because this is in the paper. So basically, and I'm going to skip some stuff and go to this thing. So if you shoot a laser beam through the polymer solution, you see this thing that works. It decides to do it. Welcome to Microsoft Edge. Which option do I want to do here? This should just be a web page. I don't want to stay up to date. I want to start without my data. Why is it doing this to me? That's great. I love this. How could you not like it? What happened to my whole thing? All right, let me try this again. This is just a web page, right? Let me hold on. Here, I have the, it's a YouTube. Yeah, this shouldn't be so difficult to do. Usually, all right, this is the web page. All right. Then I want to go here. And just put this here. All right. Hopefully this works. Yes. All right. So, all right, you shoot the laser beam through a solution, and then you see this. You can see it's like flickering, right? Like the light's flickering here. So, all right. So that's the basis of this whole show here. So,
if you're a homeowner in Ohio and you're still paying for your electricity, then I've got some big news.
definitely still paying. All right. So we got this. All right. Is it trying to focus? There. All right. All right. So you have your stuff. Shoot a laser. So it's coherent, meaning that the things are in phase. They don't decay. It's got a coherent length of like microns. That's big enough for you, because you're going to pick up over here at some angle. You're going to get some Q factor, and Q's 2 pi over the size by Bragg's law. Right, and then at that point, so you're kind of measuring things at the size scale R, which is 2 pi over, or which is Q, 2 pi over Q. Right, and then what's happening is, so you're saying like if I have a particle at the 2 points, then I get intensity over here. And if the particles aren't at the same point, then I don't get intensity. Right. So as the particles are flying around here with KT, they're just randomly zipping around by Brownian motion, then you can get, sometimes you get that and sometimes you don't get that. So the signal you get is going to be like this, like some kind of noise pattern. I is a function of T, it's some Q. Q is related to some R, some size scale that you're observing the transport over. So you're observing diffusion of the particles. So the mean squared displacement of that's going to be like that, right? Some time. So you have, so from observing this, so this is time, and you're going to say, well, at long time, at very long time, there's no correlation. In other words, at long time, I'm just getting the average concentration of the system, right? Some average. And then at short times, because if you take long times and you average over any starting point, you'll just get a number, right? But if I take short times, like I take the time 0, then I get 100% that I see the thing, right? Because I'm always in the same spot, so it's 100%, it has the same value. So if I take the intensity at 0 or time 1 and intensity at time 2, and then multiply those two together, then, and I normalize by the average, I take that and I normalize by the average of time 1 and time 2, then I'll get a value of 1 at very long distances. So that becomes the averages when T1 minus T2 is big. And when it's small, I'll get
I guess the meter is 10.
I'm sorry. Oh, that's weird, huh? There's something weird with this thing. Maybe that's better. All right, so
the screen, maybe.
yeah, anyway, so the way this is going to behave is that if I plot this correlation of this, so I measure this thing, but then in order to get the average, I'm going to have this delta T, T1 minus T2. I'm going to have to do every possible starting points on it and sum those up. And there's like So if you do that for every time, you're gonna have delta t. You're gonna find out at the short time, it's gonna be like some number, but it'll be the average of it. So if I take the ratio of that, it's gonna be 1, and it's gonna decay down to 0, basically, at the large end. There's a fluctuation. So I have 1 for the average, and I'm gonna have this fluctuation. So this is called G1 is the fluctuation. G2 is what you measure, like 1 plus G1 of time. So G1 is the fluctuations about the average, G2 over the average of the intensities you're observing. Then I can see this decay function, right? So that decay function is like as an exponential decay in time, and it's got a relaxation component to it. So it's an exponential decay. This kind of correlation of that thing. So this is the correlation function G1, and then this is the tau that you get from that. So it turns out this is a very easy experiment to do if you have two things. So you need to have a laser that's coherent. You can't do this with a light bulb because you don't get the speckle pattern of the light bulb, because you have to have coherent radiation. You don't have that. So you can get coherent from a laser or from a synchrotron, right? Synchrotrons have coherent X-rays, and this is coherent light. And the Q will be different. So different size scales of this relaxation time. And then you have this guy, there's random diffusion that's going on. So you swap out time for this relaxation time, and then you can get the diffusion coefficient because you can measure that fluctuation. That fluctuation is going to be 1 over Q squared. Right, so you can get the time tau. Tau is going to equal 1 over Q squared times 2D. Right, so from this measurement, so then you need the coherent light laser. Then you can do this. The first time they did it with a computer, they took the data for 2 hours, fed it back into a computer, did all these averaging, and took them like a week. It's kind of useless. It took them a long time to do that, especially because there's another way to do this. The particles are moving around, so you can get a Doppler effect. So if you come in with a single wavelength, when it goes out, it's going to have two. It'll have like lambda minus something and lambda plus something. So you can get the Doppler effect, and you get the energy of the particle from that, from the energy, like 1/2 mv squared. You can get kind of the diffusion coefficient of the thing, right? So was called quasi-elastic light scattering. And this is called dynamic light scattering, but now they're both called the same thing now because this isn't done anymore. Okay, so this could be done instantly, but you need to have super high resolution of the wavelength, which was difficult to get. You couldn't get it good enough. So it's an instantaneous measurement, but experimentally it's difficult to do. This thing is trivial to do experimentally, but the analysis takes a week. So they figured out how to do on the fly, make a computer chip that would do this called a correlator. So we'll do it as you watch it. It will do this thing that would take a week before if you shoved it through a computer, right? So the correlator is a separate board in the computer. It's like a video card that allows you to do whatever video games, right? So, but in this case, it's just doing this one calculation of correlating, finding the correlation function, and then spitting out this decay curve, and then gives you the tau. And from the tau, you can get the diffusion coefficient, and then you use the Einstein-Stokes equation to get the hydrodynamic radius, because you know the temperature, and you can do 6 pi viscosity times the hydrodynamic. So you can get the hydrodynamic from that. Right? So it's a simple measurement. It's absolutely so simple. Right, and the machine to do this isn't that, it's like 10 grand or something, maybe 15. Right, so it's cheap, simple to do. You get the hydrodynamic radius spits out of it, and you can do multiple decays. So you can have like one decay, another decay, another decay. See, that's called culminant analysis. So you can do a bunch of decays, and you get actually the polydispersity in RH. You'll see this paper. He comes out with actually a curve for like RH versus or number versus RH. It's like a curve like that. So you can get it. I mean, it's advanced quite a bit. That you can get multiple multimodal size, whatever you want from that. So anyway, so I'll talk a little bit more about that, but we needed to kind of go through a little bit of it for this thing on Friday, the paper on Friday. So this guy, Paul Russo's guy. There's some stuff in here about like what a correlation function is. So you don't just use correlation function for this time, for this intensity thing. Use it all over for everything. For instance, like if you're making plastic bags, and then you want to know like how well did the pigment mix in. So you can do an optical analysis of the stripes in it that come out. You can do a correlation function on those, and you can figure out the correlation length of the separation of the stripes in it. This is how you, this is basically kind of how you'd analyze if you're manufacturing something, how you'd analyze the homogeneity of like the thing coming out. Because you have kind of a random mess. You want to get a number out of it, you can spec that number. The bags have to have this correlation length. So it becomes like a spec for mixing things. Right. So you do the same thing. You like take points and then say yes or no. Is it the same stuff? Do it with different lengths over the entire sample, and then you figure out this same kind of exponential decay. Instead of over time, it's over size, and you get this correlation size out of it. Right. So there's a lot of places where you would use this kind of approach to look at and you can get other numbers from the correlation, from this correlation function. They can get the averages about the thing. So you can distinguish between different kinds of distribution of stuff. Right. So it's the same function. It's used over and over again. Right. So this is just, in fact, the correlation function is the transform of the scatter intensity. So for static scattering, you use a correlation function. For dynamic, use a time correlation function. It's the same function. It's the same idea. Right. So anyway, and you're always going to kind of be looking at some kind of transform of it like this. This is this guy that does this, but this is when he was younger. This is when he's now, actually, this is still a few years old. Now I think he's retired. So, but it's kind of funny how people change. Brownian motion. This is his slides. This is Paul Russo. He was at LSU and he was at in Atlanta, Georgia Tech, I guess, but now he's in Colorado, where he was from, like hanging out skiing or something. All right. So one thing is that, so when you get this data from this machine, it's kind of like, it can look like this, right? So this is a log plot of the time correlation function. It'll show you the raw data. This is a Brookhaven DLS machine down in the lab down in Characterization Center. That's the noise data. And then in real time, it's spitting out this curve, which will improve as you run it. In other words, it'll get, because when you get to longer times, then you get a shorter frequency on this. So that the low end will grow as you run the thing. So it's doing it real time. The calculation is doing it really intense, but it's basically doing it real time. So you can see there's an exponential decay here, basically one, that's going to give you one hydrodynamic radius. There might be another one out here. So it can fit those two, or it can get polydispersity from that curve just in the software. But if you plot it, so there's different ways to plot that. So that would be like log. You could also, this looks more like an exponential decay, right? So it's just like, that would be a linear plot. Then you can do linear log, or you can do semi-log, log linear. Log linear would give you a straight line. So you'll see, this can get confusing. You see this in a paper, they might plot it different ways, and this might be the one that you're used to. This looks a lot like a scattering curve, like a static scattering log plot. So exponential decay looks like kind of a knee. So time would be where that knee is. If it's this plot, the time is where the inflection point is. If it's a linear log plot, if it's a log linear, the slope is a time. And if it's this thing, you get the exponential, where time equals tau is where you have E. So 37% is like 1 over E. 1 over 2.71 is 37%. So 1 over E is where your tau is. So, and since tau is 1 over Q squared, again, when you have size squared, that's Brownian motion diffusion. So this Q squared thing means Brownian motion. So so you talk the culminant thing is 1 over tau. Gamma is 1 over tau. So then that's gamma is going to equal 2D times Q squared. Right, so then you can plot that to get the diffusion coefficient and get the hydrodynamic from it. So that's about, I'm going to go through this again, like, but basically you need something about this for the homework. Because he does a lot of dynamic light scattering. He does GPC, which I already talked about. And on the GPC, he has a dynamic light scattering. And on that thing, he also gets static light scattering and viscosity. And he gets index of refraction measurement. So he's quantifying these dendrimers, doing all that stuff. So I'll go through that on Friday. Anyway, any questions? Or it's kind of a lot of stuff, but hopefully it's okay. Hopefully it'll come together with that paper. Stuff together. So okay. Oh, this guy off.
For you. Just weeks ago, the federal government.
I know about that. Goodbye. Pull the ripcord.